This is part 2 of lecture 2.1 of Math 108, Direct Proof of a Conditional Sentence. In this video, we described direct proofs of other variations of a conditional sentence. You are expected to have watched part 1 before this video. Consider a claim which is a conditional sentence whose consequent is a conjunction of two or more sentences. A direct proof of this claim still follows the general outline, which begins with the assumption P and ends with a statement Q1 and Q2. However, the proof has the following more detailed structure. Recall from a previous exercise that the propositional form P implies both Q1 and Q2 is equivalent to the conjunction P implies Q1 and P implies Q2. Hence, to prove that P implies both Q1 and Q2, we need to prove the two statements P implies Q1 and P implies Q2. So a direct proof of the claim P implies both Q1 and Q2 consists of two parts. First, a direct proof of P implies Q1, and second, a direct proof of P implies Q2. Notice that in this type of proof, the assumptions in the different parts are the same, but the conclusions are different. Compare this with proof by cases, which we introduced in part 1. To minimize repetition and to make our proof more readable, we state the assumption P only at the beginning of the proof. This condition P is assumed to hold throughout the proof, even when not explicitly stated. Also, if the proof is short enough, we do not need to write the labels part 1 and part 2. For example, consider the claim, if A equals C and B equals D, then A plus B equals C plus D, and A times B equals C times D. Let P1 be the sentence A equals C, P2 be the sentence B equals D, Q1 be the sentence A plus B equals C plus D, and Q2 be the sentence A times B equals C times D. Then the claim is a conditional sentence whose antecedent is the conjunction P1 and P2, and whose consequent is the conjunction Q1 and Q2. To prove the claim, we need to prove that if A equals C and B equals D, then A plus B equals C plus D, and if A equals C equals B equals and B equals D, then A times B equals C times D. A direct proof for the claim begins by assuming that A equals C and B equals D. In the first part, we shall prove that A plus B equals C times D, C plus D, and in the second part, we prove that A times B equals C times D. Assume that A equals C and B equals D. Applying the addition property of equality to the statement A equals C gives us A plus B equals C plus B. And applying it to B equals D, together with the commutative property of addition, gives us C plus B equals C plus D. Hence, by the transitive property of equality, A plus B equals C plus D. This completes the first part of the proof. For the second part of the proof, we do not need to state again the hypothesis that A equals C and B equals D. By convention, this hypothesis is understood to still hold. This time, applying the multiplication property to the statement A equals C gives us A times B equals C times B. And applying it to B equals D, together with the commutative property of multiplication, gives us C times B equals C times D. Hence, by the transitive property of equality, A times B equals C times D. This completes the second part of the proof and completes the proof of the claim. Consider a claim which is a conditional sentence whose consequent is a disjunction of two or more sentences. A direct proof of this claim still follows the general outline, which begins with the assumption P and ends with a statement Q1 or Q2. However, the proof has the following more detailed structure. Recall that the disjunction Q1 or Q2 is logically equivalent to the conditional sentence not Q1 implies Q2. Hence, to prove the statement Q1 or Q2, we shall prove the conditional not Q1 implies Q2. A direct proof of this statement begins by assuming the condition not Q1 and ends by showing the condition Q2. Observe that in this proof, we assume two conditions simultaneously, namely the conditions P and not Q1. We can combine these two assumptions into one, namely the conjunction P and not Q1. Thus, our proof could be written as follows. Assume P and not Q1 and prove the condition Q2. This is the same as showing the conditional sentence if both P and not Q1, then Q2. Recall that this propositional form is logically equivalent to P implies either Q1 or Q2. Note that in this proof, the roles of Q1 and Q2 are interchangeable. The choice of which condition is used for Q1 and which condition is used for Q2 depends on how easy or difficult it is to prove Q2 from P and the negation of Q1. For example, consider the claim if A times B equals 0, then either A equals 0 or B equals 0. Let P be the sentence A times B equals 0. Let Q1 be the sentence A equals 0, and Q2 be the sentence B equals 0. Then, the claim is a conditional sentence whose antecedent is P and whose consequent is the disjunction of Q1 and Q2. To prove the claim, we need to prove that if A times B and if A times B equals 0 and A is not equal to 0, then B equals 0. Alternatively, we can prove that if A times B equals 0 and B is not equal to 0, then A equals 0. A direct proof begins by assuming that A times B equals 0 and A is not equal to 0. We shall prove that B equals 0. Assume that A times B equals 0 and A is not equal to 0. Since A is non-zero, it follows from the existence of multiplicative inverse elements that A has a multiplicative inverse 1 over A. From the hypothesis A times B equals 0 and the multiplication property of equality, we get that 1 over A times AB is equal to 1 over A times 0. By the associative property of multiplication, 1 over A times AB is equal to 1 over A times A times B. By the transitive property of equality, we then get that 1 over A times A times B is equal to 1 over A times 0. Since 1 over A is the multiplicative inverse of A, 1 over A times A is equal to 1. Hence, by the multiplication property of equality, 1 over A times B is equal to 1 times B. Thus, by the transitive property of equality, 1 times B is equal to 1 over A times 0. Since 1 is the multiplicative identity, 1 times B equals B. Thus, by the transitive property of equality, B equals 1 over A times 0. Recall that by example 3, any real number times 0 is equal to 0. So 1 over A times 0 equals 0. Therefore, by the transitive property of equality, B is equal to 0. This proves the claim. We now turn to biconditional sentences. Recall that the proposition P if and only if Q is equivalent to the conjunction of the conditionals P implies Q and Q implies P. Thus, one way to prove the biconditional P if and only if Q is by proving the conjunction P implies Q and Q implies P. Such a proof consists of two parts. One part to show that P implies Q, which we also refer to as the forward implication, and another part to show that Q implies P, the backward implication. We can use any method to prove each of these conditionals. For example, consider the claim A times C equals B times C if and only if either A equals B or C equals 0. Let P be the sentence A times C equals B times C. Let Q1 be the sentence A equals B. And let Q2 be the sentence C equals 0. Then, the claim is a biconditional of the form P if and only if either Q1 or Q2. A two-part proof of this statement consists of the proof of the conditional if A times C equals B times C, then either A equals B or C equals 0. And the proof of the conditional if either A equals B or C equals 0, then A times C equals B times C. We shall give a direct proof for each of these conditionals. The statement if AC equals BC, then either A equals B or C equals 0 is a conditional sentence whose consequent is a disjunction. Thus, we begin our proof by assuming the conditions AC equals BC and C is non-zero. And our aim is to prove that A equals B. The statement if either A equals B or C equals 0, then AC equals BC is a conditional sentence whose antecedent is a disjunction. Thus, our proof consists of two cases. In the first case, we assume that A equals B and prove that AC equals BC. In the second case, we assume that C equals 0 and prove that AC equals BC. For the proof of the forward direction, assume that AC equals BC and that C is non-zero. Since C is non-zero, it follows immediately from the cancellation law for multiplication, which we proved in example 2, that A equals B. This completes the proof of the forward implication. We now prove the backward implication. For case 1, assume that A equals B. Then, by the multiplication property of equality, AC equals BC. This completes the proof of case 1. For case 2, assume that C equals 0. Then, by the multiplication property of equality, AC equals A times 0 and BC equals B times 0. By example 3, A times 0 equals 0 and B times 0 equals 0. So, by the transitive property of equality, A times C equals 0 and B times C equals 0. Again, by the transitive property of equality, we get A times C equals B times C. This completes the proof of the claim. We have another way of proving a biconditional sentence. Recall that for propositions P, Q, and R, if P is equivalent to R and R is equivalent to Q, then P is equivalent to Q. Thus, another method of proving the biconditional sentence P if and only if Q is by finding a series of statements R1, R2 up to Rn such that P is equivalent to R1, R1 is equivalent to R2, and so on, and Rn is equivalent to Q. It then follows that P is equivalent to Q. An example of this type of proof will be given later. The statement P if and only if Q if and only if R is a short way of writing the conjunction P if and only if Q, and Q if and only if R, and R if and only if P. You will also frequently see this written as the statement, the following are equivalent: condition P, condition Q, and condition R. It can be shown that this statement is equivalent to the conjunction P implies Q, and Q implies R, and R implies P. The proof is left as an exercise. Hence, to prove that P, Q, and R are pairwise equivalent, we only need to prove the conditional sentences P implies Q, Q implies R, and R implies P. The proof will then have 3 parts, with each part a proof of one of these conditionals. You may use any method for each of these proofs. An example of this type of proof will be given later. This is the end of part 2 of lecture 2.1. You may now proceed to lecture 2.2. Thank you for your attention.